Check. Check. That's good. Okay, let's begin. Sorry, we're a little late. Okay, I don't see any announcements other than two. Okay, one is the first midterm is a week from today, is it not? Or am I mistaken? It's going to be February 3rd, yeah, a week from today. What's on it? Everything I will have covered in class up till end of business on Wednesday. All of that will be fair game for the midterm. I do have some review problems. I'll post those. You should, treat those as just as important as homework problems. You don't turn them in, of course. And I will post some partial solutions, that is, solutions to some selected problems. Not every solution. Let's see. Programming assignments. PA3 is now posted. PA3 is by far the most difficult assignment, I think, of all the 5. It is in Java. It uses your list ADT from PA1. So it will be necessary to look that over and wring out any bugs that there might be. And also you need to make some alterations to it in order to use it in PA3. You have to change it from a list of ints. So the data field in Node will change from int to object. So in other words, a generic list. Now, if you've read it, you'll notice I'm not asking you to use the Java tool generics, right? To the so-called Java generics method of creating a generic list. Instead, I just want a list of objects, and that allows you to put any reference variable in that data field, or a reference to any object whatsoever in that data field. The reason I don't want to do that is because I don't want to make Java generics a topic that we're covering in class or something like that. I covered it very briefly in a lab in 12B, but not everybody who teaches 12B does cover Java generics. It's a little bit of an advanced topic for Java. So since I don't want to teach it, I'm not going to assume that everybody knows about Java generics. However, you do know what the object type is, the object class. It's a superclass for all user-defined types or user-defined classes in the Java language. That's the main change that you have to make to the list. The other changes are, listed in detail in the project description. I want you to start reading them this weekend. You have 2 weeks to do it because I consider it the most difficult assignment. It's difficult because you have to basically invent the algorithms to do this, to do these matrix operations in the matrix representation that I'm specifying here. So I'll let you wrestle with that. At least read the thing and try to generate some questions for me on Monday or Wednesday, and we could talk about it if you like. PA2 was extended second time, due tonight at 10 p.m., which means with the 12-hour grace period, it closes at 10 a.m. tomorrow morning. Is that going to be enough? Okay, what's the problem here? Can I answer any questions about it? Go ahead. Okay, so people are running Valgrind. So you can get the thing to work, but then you run Valgrind, and all of a sudden you find there's not only a bunch of memory leaks, but there are illegal reads and illegal writes. If anything, the illegal reads and writes are worse than the memory leaks. You need to fix all of that stuff, or you will lose points. Okay, I can't say that there are going to be a great many points lost, especially on this first one, this first C program, but you need to realize that memory management is your responsibility in C, right? You cannot rely on a garbage collector that'll clean up after anything that you left laying around. These kind of illegal reads and writes and memory leaks are not possible in Java. That's part of the genius of the language. But C is a more primitive language. And so I suggest that even while you're testing your project and you're getting wrong results, you try running it under Valgrind. Because it could be that the real reason is that the list is getting mangled or something like that. Or it's not just a matter of memory leaks, you forgot to free something. It's really some kind of mangling of the list that is causing both the wrong input or the wrong output and also the memory leaks themselves or the memory errors themselves. So Valgrind is a great tool for that. Beyond that general statement, I can't tell you what the cure is for your problems, right? There's no algorithm for programming. Can't give you an algorithm to write a good program. If that were the case, there would be no programming jobs because somebody would have typed up a program to write all future programs and you guys wouldn't even be here. Okay, so that's why you're here, because you need to learn that it takes intelligence to figure things out. Does anybody notice the irony in that? I do, anyway. Okay, so are there any specific questions I can answer? Other than that general stuff about memory leaks and Valgrind. Go ahead.
I had a couple of problems with the naming of two functions, which is index and clean.
Uh-huh.
They have a very specific name, maybe a keyword.
Okay, so let me ask you something. What compiler are you using? It's Xcode. So is that an IDE that you got, and it's actually a C++ compiler, isn't it?
It has various. It's a Mac IDE.
Well, name conflicts with the function name index and anything else, in my experience, have always come about because somebody is using a C++ compiler. Now, it might be advertised as a C++ compiler, but the fact is it's just one compiler. In C++ language, there is an existing built-in function called index, and that's going to cause a name conflict. However, I wouldn't develop under that. I mean, most good IDEs, like Eclipse or something like that, have different plugins for different, at least I think they do, for different compilers. Find a plugin that specifies it's the GCC compiler with the dash standard equals C99, right? The C99 standard, and you won't get that. Question?
Relating to his, even if you use GCC on a Mac and you have Xcode installed, you'll still get that conflict.
Okay, so are you doing dash standard equals C99?
Yeah, I'm using the makefile unit. It works on the timeshare, but if you try it on a Mac,
You try it on a Mac. So I see. So it's not an IDE. It's a just standalone compiler that runs on a Mac, and for some reason it is. Okay, so I would. It's possible to install GCC on a Mac. On any Unix system, you can install a GCC as opposed to some other compiler. But that's a little bit beyond the content of the course, telling you how to set up your own platform. I figure it's my job to tell you one correct way to do things, and that's on the timeshare. It's great if you can do it in a consistent way on your own personal platform, so you don't have to be hooked up to the network or the internet just to be able to do a compile or something like that. But there are workarounds. It's almost always, in my experience, it's always the compiler problem. It's not the right compiler. Go ahead. It is not okay to change the name of the method. So I hope everybody knows why. The reason it's not okay to change the name of the method is because These are modules, and they have a specific interface. You are not to change the interface. The interface is predetermined. That's what I gave you. The job is not really, I mean, same thing I said in Java. I mean, if the problem was to sort an array of strings, heck, you could have done that back in 12a. The problem is to build an ADT module with a specific interface. So I should be able to take one person's list.c, one person's lex.c in my make file, put them all in one directory, hit make, and the whole thing works perfectly. But if people start changing the names of functions, they're changing the interface, changing the signatures of functions also, inputs and output types. They're changing the interface, and it's not the same module, right? It's a different interface. So no, it's not. Yes? The question is it fine to add functionality to the make file? Like what? That's a good, I would consider that good functionality, a mem check, or call it check. I saw somebody had check 1 and check 2. Check 1 would check lex for memory leaks in running lex on a specific pair of input and output files, and then check 2 would just be check memory leaks on list client, right? So I guess it may be reversed. Check 1, you're using list client or your own list test to look for memory leaks in your list ADT, and once you're sure that the list ADT is watertight, then you can go on and start looking for leaks that are specifically in your Lex code. Question?
It wasn't a question, it was if she has a problem with the naming, can she change the function name temporarily to see?
Temporarily? Yeah, sure. I mean, what you...
Because you're not looking for the compiler.
Right. As a diagnostic technique, you can do basically anything. So if you want to temporarily change, see if that was the problem, and then start looking for, see what the problem is with the compiler on your platform, that's fine. But the one you turn in, let me put it this way. You'll lose points if the function names are not spelled correctly to the letter. You will lose points if the one you turned in has misspelled anything. Question? How should you be comparing strings? Okay, so in Java, it's the string function compare to. It's an instance method. Instance of string dot compare to is a negative number if the first instance is alphabetically earlier than what's in parentheses. All right, that was how string dot compare to worked. So the equivalent of that works pretty much the same way is strcmp, strcmp. Now, if you've never heard of that, I do have a link down here. Does everybody see that? Here's a C library reference. Here are several. What I would wish there was a sort of a comprehensive reference to the C language the way there is to the Java language. Unfortunately, it's nobody's job, like the Oracle corporations, to post such a thing. So there are a few, but they're all kind of incomplete. For instance, the C reference guide is really good, but notice it's from 1997, which means it's not even C99, which is the version you're using. However, it's pretty good. And it tells you pretty much everything you need to know about the standard C library functions. So if you just, let's see, Control F, strcmp, I get to the strcmp function, and strcmp, there it is. They don't say much about it, but at least it's something. And it might actually, by the way, you could also use the man pages in Unix, right? Do man strcmp. Because the C language is, in a way, it's part of the background information for the Unix operating system. So standard C functions are explained in the man pages. Okay, returns an int, first string, second string. So it works exactly like strcmp. Instead of putting instance of string dot it works just like compare to. So instead of putting the first string and then a dot and then function name, just put function name, open paren, first string, second string. And you should think of them as kind of like an inequality, right? If the first string is less than the second string alphabetically, then it's going to be a negative number. If it's greater, that's going to be a positive number. If they're identical, you'll get 0. That'll be the return value of the int. And when I say string, what is a string in C? A string in C is a char array that is terminated by the null character. Right? A null terminated char array is what we mean by string in the C language. That's what the string library works with. And by the way, you have to #include string.h to use any of these functions. Okay, does that answer? What else? Nothing. Okay, so let us pick up where we left off last time. Where did we leave off? I was talking about logarithms. Yeah. Logs. Okay, so let's start with this equation again. X equals a to the log base a of x. That's just a fancy way of writing x. A fancy way of writing b is b to the log base b of a. That all to the log base a of x. Okay, so that just gives you x. Two different bases, a and b. So if I just take log base b of both sides, I get this equation. Log base b of x. That strips off the exponent base b here. So I get, oh wait, I forgot one thing. Laws of exponents. I can multiply, I have a power to a power, so I can multiply this times this. So I get b to the power log base b of a times log base a of x. So if I take log base b of both sides of this equation, I get log base b of x equals log base b of a times log base a of x. Okay. Let's just stare at that for a minute. We're going to come back to that, so I'm going to refer to that as star. So the variable here is x. A and b are fixed constants. So that is nothing but a constant. In fact, if I use n as the variable, which is what we usually do in this class, log base b of n is equal to log base b of a times log base a of n. And we notice that is a constant. And these two bases are completely arbitrary. So any log function is a constant, some constant times every other base, every other log function. So therefore, log base b of n is theta log base a of n. Every log is a constant times every other log. All you do is change the constant. The constant depends on the two bases. And remember, this was an exercise early on in the last handout. Show that if you take a function and you multiply it by a constant, the result, and it doesn't matter what the constant is, as long as it's positive, the result is big O, big omega, and theta of the original. So in other words, as far as asymptotic growth rates are concerned, there's only one log function. Notice that's the opposite of what's true for the inverse of the log functions, the exponentials. We saw as one of the exercises in that handout that the bigger base wins, right? In an exponential function, The exponential function with the bigger base is the winner, asymptotically speaking, I guess I should say. Or if it's an algorithm, it's the loser, right? It's the one that the faster growth rate is the bad algorithm. Okay, so only one log function. Therefore, when I write things, in some kind of asymptotic formula involving logs, I almost always will leave off the base and just write log, theta log n, because the base doesn't matter. One more thing that's nice about this formula is I can write it like this. Log base a of n equals log base b of n divided by log base b of a. This is a nice conversion formula from one base to another. If you have a calculator that only has a log base b button and doesn't have a log base a button, and you want to calculate log base a of something, just take log base b of the something divided by log base b of a, the base you want to convert to. So you really only need one log button on your calculator, even though you have the ability to insert any base you want. What else? Let's go back to star and use both sides as an exponent on A. So A to the log base b of x equals A to the power this thing. I'm going to reverse the order of the factors. A to the log base a of x, no. A to the log base b of x, yeah. A to the log base a of x times log base b of a. All I did was I swapped these two, and I used both sides then as an exponent on a. But laws of exponents says that this is a to the log base a of x all to the power log base b of a. Okay, but the thing in parentheses is just a fancy way of writing x. So I get a to the log base b of x equals x to the log base b of a. In other words, this function, let's think of b as fixed now, a and x as the variables. Sorry about that, I have a cold or something. As a function of two variables, this is a symmetric function. You can swap them. I mention this because it's going to be algebraically useful to do that at some later point. So a couple of things I want you to remember. I want you to remember this, and I want you to remember this. Okay, last topic in this handout, Stirling's formula. So let n be a positive integer. Then Stirling's formula is an asymptotic formula for n factorial. N factorial is equal to square root 2 pi n times n over e to the power n times 1 plus theta 1 over n. So this is, believe it or not, a very useful formula. The reason it's useful is because we have a lot of, we don't really like algorithms that run in factorial time, but factorial functions show up in algorithm analysis. And we like to know how fast those, how those functions grow. This is a much better algebraic expression than n factorial, believe it or not. Because this is kind of hard to work with algebraically. What it has in it that we don't like is this asymptotic notation. Well, we shouldn't not like that. We should like that. But what does this stand for? What does that term stand for? You've learned that now. I've said it a couple of times. Say again? Yes. It's this. That's right. So this term stands for some function that I don't care to give a name to that decreases, goes to 0 at the same rate that 1 over n does. That's what it stands for. It's not 1 over n. It's not necessarily a constant times 1 over n, probably more complicated than that. But the point is that this function goes to 0, and it's very specific as to how fast it goes to 0, just like 1 over n. So this thing in parentheses, you should just in your mind think of that as just very close to 1. For large n, this is very close to 1. So for large n, the expression on the right is very close to n factorial. Another way of looking at it is I could solve this equation for this term, right? Divide both sides by that factor, then pull the 1 over to the left. That would isolate this term. The theorem is that the ugly function that I get, involving n factorial, square root, exponentials, and so forth, that function would go to 0, like 1 over n. Question? Yeah, that's an e. Yeah, sorry. That is the base of the natural log. E, that number e. I mean, there might as well be where did e get in there? You might just as well ask, how did pi get in there? But it's in there. Now, I would like nothing more than to just divert us into a proof of Stirling's formula, but it would be outside the scope of the course. We wouldn't learn that much about how to prove things, and I wouldn't ask you to memorize that proof. What I do want you to be able to do is to use Stirling's formula. So let's look at some corollaries. First of all, part A, n factorial is little o of n to the n. Now, if you think about it, that's kind of obvious because this is a product of n factors, all but one of which are less than n. This is a product of n factors, all of which are equal to n, which is bigger. So all the factors except for one are bigger here than they are here. So it makes sense that this would be a faster growing function than that function. Nevertheless, that's just a hand-waving argument, right? That doesn't prove anything, doesn't prove the limit, for instance. Suppose I said n factorial over n to the n, right? That would be hard to establish that the limit is 0, because you certainly can't differentiate n factorial. Here's another one. N factorial is little omega of b to the n, and it doesn't matter what the b is for any b greater than 1. Okay, so this establishes where the factorial function sits in the in the hierarchy of growth rates. At the bottom, we have the log functions. And in the middle, we have the polynomial functions. And as we saw, above those are the exponential functions, right? Exponentials, and it doesn't matter what base. The winner is always the bigger base. But above all the exponential functions is the factorial function. And above the factorial function is the n to the n functions, a function of that form, a power, a variable where you have a variable in the base and the exponent, and both are growing. So this function is above this, which is above exponentials, which are above polynomials, which are above log functions. There are a lot of complex functions in between, in this grand hierarchy. We're just getting used to it. Here's a very curious and useful corollary. Log n factorial is theta n log n. N log n. How would you have guessed that? Because after all, the factorial function is a very fast-growing function, faster than any exponential. On the other hand, the log function is a very slow-growing function. So we have a composition on the outside, a slow-growing function, on the inside, a fast-growing function. It's kind of a tug of war. Where does it land? How fast is the result? How does that thing grow? This is how fast it grows, n log n. So that's a polynomial, that's a log. You should always think of a log as being infinitesimal compared to a polynomial. So what this says is it's infinitesimally faster growing than n to the power 1. That's kind of the way I think of it. Informally. Okay, all these can be proved using Stirling's formula. Let's do one. Proof of one. Take the limit n factorial over n to the n. Well, if I didn't have Stirling's formula, I'd be stuck. Stirling's formula allows me to replace n factorial by this expression. Square root 2 pi n times n to the n over e to the n times 1 plus theta 1 over n, all over n to the n. I'm sure a lot of people are looking at that factor and saying, oh my God, that is the ugliest thing I've ever seen. I don't want that. Make that go away. But that's actually nothing. We're going to take a limit. In the limit, that is just 1. That's all. The notation just tells us how fast it goes to 1. That's all. All right, so we get to cancel n to the n, top and bottom. So we end up with this thing. Square root 2 pi times, actually let me write it like this. Square root 2 pi times square root n over e to the n times 1 plus theta 1 over n. Okay, that's a constant. That has limit 1. What's the limit of that as n goes to infinity? And by whose rule? What do you see? I see a polynomial. I know you don't usually think of that as a polynomial, but anything of the form n to a power, in computer science we call that a polynomial. That's n to the 1/2. To a mathematician, it has to be n to an integer, but to a computer scientist, it's a polynomial growth rate because it's n to a power. Polynomial over exponential. Who wins? By L'Hopital's rule. How come everybody's... I can hear you breathing out there. I hear a little rustling. Who wins? The exponential. The bottom blows up, faster than the top blows up. So this is going to what? 0. That's a constant. That's going to 1. So what's the limit? Huh? 0. So the top is what of the bottom when the limit is 0? Little o. N factorial is little o of n to the n. Somebody said big O. Yeah, that's true too. That's only because little o is a subset of big O. Okay. End of proof of A. Oops, I should have said A here. Okay. What about... Yes, go ahead.
You said that theta 1 over n goes to 1.
No. Theta 1 over n goes to 0. If I add 1 to that, I get something that goes to 1.
I thought by the limit theorem that any theta function has to go has to be greater than 0 but less than infinity, right?
Yeah, 1 over n is greater than 0 for all n. Its limit is 0. So yeah, I mean this is a strictly positive function, but it's also strictly decreasing, and it goes to 0 in the limit. I know we didn't really talk about any examples where the limit of the function was anything other than infinity. We're really talking about the rate at which a function blows up. But the same definitions all hold, and can talk about, you can use them to compare the rate at which any limit is approached, including 0. Okay? All right, so next, so I'm going to skip B and do C. Proof of C. Okay, so let's make sure we have Stirling's formula handy. And what was C? C was log n factorial is theta n log n. So let's take the outside divided by the inside. Log n factorial. I'll tell you what. Let's start with log n factorial and then divide by the inside. So let's just take log of both sides of Stirling's formula. Log n factorial. Well, let's apply the laws of logarithms. Log of a product is what? Huh? Addition, right. Log of a product is the sum of the logs. So this is log of square root 2 pi n plus log n over e to the n plus log 1 plus theta 1 over n. Now, log of a sum, is there a formula for a log of a sum? Is there some law of logarithms that allows you to simplify that? Log of a sum, what's that equal to? It's a trick question, guys. There's no way to simplify that. I don't usually ask trick questions, but I couldn't resist that one. Right? Log of a sum, there's nothing, right? You cannot simplify that. Don't start writing the sum of the logs, okay? That doesn't simplify. However, this term is, there's nothing, absolutely nothing wrong with that term, right? As n goes to infinity, that goes to 0, so the thing inside the log goes to 1. Log of 1 is what? 0. So this term is going to go to 0, okay? Let's simplify this further. So this is square root 2 pi times square root n. So this is log square root 2 pi plus, because it's multiplied here, log n to the power 1/2. And this is plus, this can be brought out in front, n log n over e. Log of something to a power, you can bring the power out in front, plus log 1 plus theta 1 over n. What else can we do? Well, that's just a constant. Let's leave that alone. Log square root 2 pi plus 1/2 log n. Bring the power out in front. And log of a quotient is the difference of the logs. So this is n times log n minus log e. And then let's distribute the n. So this is plus n log n minus n log e. Right. So I did two things. I took log of a quotient is the difference of the logs, then I distributed the n over the difference. Plus log 1 plus theta 1 over n. Good enough? Well, that's a nice expression. It allows me to figure out what the asymptotic growth rate of log n factorial is. Informally, we should look at this and say, what's the highest order term? That one goes to 0. That one's constant. That's a constant times log. That is n times a constant. This is n times log n. This is the highest order term. So you can see informally that log n factorial has to be theta of the highest order term. However, I don't consider the proof quite complete until we use the theorem. So let's take log n factorial over n log n. If I do that, divide each term by n log n. What do I get? Constant log square root 2 pi over n log n plus the log n's cancel, so I get 1 over 2n plus n log n cancels n log n, I get 1, minus the n's cancel, I get log e over log n plus the ugly thing, log 1 plus theta 1 over n log n. Okay, the bottom blows up, the top is constant. That goes to 0. Same thing here, that goes to 0. This approaches 1 because it's a constant. Constant over log n, that approaches 0. And this one, denominator blows up and the top goes to 0. This goes to 0 faster than anything else. So the limit as n goes to infinity of log n factorial over n log n is equal to 1. And 1 is in the range 0 to infinity, not including 0 and infinity. So, what do we conclude from that? What does our limit theorem allow us to say straight off? The top is what of the bottom? Okay, you're forgetting the theorem. That's a bad place to be in, especially on the exam, guys. Memorize the theorem. All right, so this says, therefore, that log n factorial is theta n log n, which is what we set out to prove. Don't forget the theorem. If you take a limit of a quotient and you get a real number, not 0, not infinity, the top is theta of the bottom. We proved that. Notice all throughout I've been unspecific as to what the base of this log is, of course. I can't remember the last time I taught CS 101 and this didn't appear on some exam, either midterm 1 or the final exam. Okay? Here's an exercise that's in the handout. This is something else that I tend to put on exams. Actually, I think it's a homework for next week. 2n choose n is equal to theta 4 to the n over square root n. Now, the bottom here is polynomial, the top is exponential. Remember, polynomials are like infinitesimals when compared to exponentials. So this is a growth rate which is infinitesimally weaker than 4 to the n. And that's how fast this function grows. Oh, by the way, what function is this? Recall what m, they use different letters, m choose k stands for. That's not a fraction, guys. I didn't leave out the fraction bar. That's m choose k. This is the number of k element subsets of an m element set, say m set. You have a set with m elements in it. How many k element subsets does it have? That's the definition of this symbol. And in CE16, you prove this formula, m factorial over k factorial m minus k factorial. A bunch of factorials in that, isn't it? Huh? So this is the number in the mth row kth column of Pascal's triangle, right? Mth row of Pascal's triangle, march over k from the left. Start your counting at 0. So this is one of the numbers in Pascal triangle. So what I'm saying here is take the sequence 2n choose n. 2n choose n is the sequence of numbers smack down the center, the axis of symmetry of Pascal's triangle. So if you just write out Pascal's triangle as forever, and then circle all the numbers right down the middle, that's a sequence. That is this sequence, and this is how fast that sequence grows. Okay? And that's what you're asked to prove. You can see where Stirling's formula comes in because there's a bunch of factorials in it. And a bunch of algebra, right? There's going to be and you're actually going to use Stirling's formula on each of these three. Okay, I believe that's a homework problem for next Wednesday. I think you're all ready to have at it now. Okay. Okay, now what? Next handout, induction proofs. So this is the one handout that doesn't correspond to any particular pages in the book. I don't think they have anything in the book on induction proofs. They might say something about it in the appendices. Okay, so what is induction? I consider this to be at least your second time through the technique of mathematical induction. Nevertheless, I'm going to start from scratch. So let P of n be a propositional function. A propositional function. So what does that mean? That means a function whose input, we'll say, of an integer n. Usually a positive integer, but in general it could be any integer. That means what goes into the function is an integer, and what comes out is a statement or a sentence or an assertion, a proposition. There are lots of statements, right? What distinguishes a proposition? Propositions are statements that can be evaluated, at least in principle, as true or false. It would make sense to assert that P of 6 is either true or false. Hello, that's an assertion which is neither true nor false. There are a lot of sentences that don't meet that. In a way, you could think of this as a Boolean function, right? Input is integer, output is either true or false, one of two values. Okay, so so mathematical induction seeks to prove propositions of the following form. Theorems of the form for all n greater than or equal to some fixed value n naught p of n. So it's some assertion that P of everything beyond some, for all n beyond some point, P of n is a true statement. Usually n naught is 1 or 0. Okay. So this is the goal. Prove that statement. I want to stress here that P of n itself can be anything. Any assertion that involves an integer parameter, n. Okay, so there are many, here's an outline of how one way to do an induction proof. One, what you do. Step one is the so-called base case, or base step. Show that P of n naught is true. The first in the sequence of true statements, the infinite sequence of true statements, is true. And then 2, there are many variations on this step, so I'll call this 2a. This is the induction step. Show or prove for all n greater than or equal to n naught, if P of n is true, then P of n plus 1 is true. So to carry out this plan, first you pick out one of the infinite sequence of sentences you want to show that are true. Pick out one of them and show that it's true. Often this is just a fact of arithmetic or some triviality of the definitions. And then show that for any n greater than or equal to n naught, if P of n is true, if the nth sentence in the sequence is true, then the very next sentence must also be true. Very helpful to visualize this as a domino analogy. So you have an infinite sequence of dominoes that are lined up and ready to fall. You've all seen these things posted on the internet, right? Millions of dominoes. Well, imagine somebody had the time and patience to line up infinitely many dominoes. Couldn't really do it, but let's just imagine that it was done. Here's the nth domino, the n plus first domino. Now, there might be some initial dominoes before the n naught, the one indexed n naught, but we don't care about those, right? We're not trying to prove anything about the dominoes indexed lower than n naught. They might fall, they might not fall. Some of them might be glued to the floor. Some of them might fall for other reasons, but that's not part of the proof. So, in this analogy, P of n is the statement the nth domino falls. Okay, so if that's P of n, what is 1 P of n naught? P of n naught says the n naughth domino falls. Two, 2a says, what are we trying to prove? For all n greater than or equal to n naught, P of n implies P of n plus 1. In other words, let's try to translate this into English. First, let's do it mechanically. For all n greater than n naught, if the nth domino falls, then the n plus first domino falls. Let's try to translate it in English without using the word n, right? Without naming the variable n. Can you figure out a way to say that? No? You know, in CE16, I spend a lot of time trying to get people to learn how to translate logical sentences written in logical symbols into the English language, colloquial English, and then back again. You need to learn how to do that, right? And not just recite it sort of manually, but actually say it the way a human being would say it. Question or answer?
So for every domino that exists, there's one domino within them. So there's one domino within all the dominoes that exist. If all of the dominoes fall, then there's one domino in front of that one that falls.
That's not quite right. I mean, yeah, go ahead, try.
Okay, so there exists a domino such that if you tip over that domino, any domino greater than or any domino that is past that domino or that domino itself will fall. So
Okay, still a little off base. I hear both of you saying there exists. There's no existential quantifier in this. Well, let me translate it in the way I would say it. It says, if any particular domino falls, I won't even say particular. If any domino falls, then the next one also falls. Right? I didn't use the letter N in it. So how do I say any? It's the for all. For all says, for any index, if the domino at that index falls, then the next one also falls. That's the way you should read this. Question?
Do you care whether we use strong or weak induction?
I do care if you use strong or weak induction. Right? So some theorems want to be proved by weak induction. You should prove it by weak induction. I will say a lot about strong and weak induction, so you're getting a little ahead of me right now. But because this is weak induction. I haven't talked about strong induction yet. We will. All right, so if any domino falls, then the next. Now look at these two. The first domino falls, or the first index, one index to n naught falls. And then if any domino falls, the next one falls. Our conclusion from that is for all n greater than or equal to n naught, P of n. Somebody translate that. There's no if in this, and there's no there exists in this. All dominoes fall. Thank you. All dominoes fall. You should try to translate these symbolic-looking logical things into ordinary English. The more you do that, the more you'll understand what you're looking at. So, forget the logical notation. The first domino falls. If any domino falls, then the next one falls. Conclude all dominoes fall. Does that make sense to you? All right. Nevertheless, we need a new inference rule, right? I need a principle to allow me to make this inference from the first domino falls and from if any domino falls, the next one falls, to then conclude all dominoes fall. It seems reasonable. We ought to be able to make that inference. But we need an official inference rule to do that. The reason we need that is because if we try to set this up as a proof, the proof itself would be infinite, right? The first domino falls. If any domino falls, the next one falls. Therefore, the second one falls. So the second one falls. But if any domino falls and the next one falls, therefore the third one falls. So the third one falls. But if any domino falls, the next one falls, so therefore the fourth one falls. So the fourth one falls. Right? That's a proof. The only problem is a proof is supposed to be a finite thing. Proofs are a finite sequence of sentences. So we need a new inference rule in logic to allow us to, from this and this, infer this. Right? That inference rule is called the principle of mathematical induction. Actually, this is called the first principle the inference rule expressed here is called the first principle of mathematical induction. It's also called weak induction. It's called weak induction to distinguish it from something else called strong induction. And that strong induction is the second principle of mathematical induction. I'll usually abbreviate this PMI, principle of mathematical induction. Okay, before I talk about strong induction, let's talk about another a way to reparameterize this. So, another form of weak induction I will call first PMI. I'll call that 2B. The base case is identical. So instead of the induction step, instead of being this, it is to show for all n strictly greater than n naught, P of n minus 1 implies P of n. All this is a reparameterization. It's a shift in the variable, right? It's a renaming, a reindexing of the list of variables, or the list of propositions to be proved. So, using the domino analogy, this is n minus 1, and this is n. So here in the induction step, I show that if the nth domino falls, the n plus first domino falls. And I show that for all n greater than or equal to n naught. In this case, I show for all n strictly greater than n naught, if the n minus first domino falls, then the nth domino falls. If you translate it, it says the same thing. If any particular domino falls, then the next one falls. Why the strict inequality here versus the weak inequality here? Strict inequality is necessary because if n were allowed to equal n naught, then n minus 1 would be n naught minus 1, which is one of the dominoes that's either glued to the floor or I don't care about. Those are the off-limits dominoes before the n naughth one. All right, so that is another form of weak induction. But there's also something called strong induction. Variations. Yeah, I know. You guys are watching the time closer than I am, aren't you? Okay, so we'll talk about strong induction next time. Please read all of this handout. I want to go through it quickly on Monday because you need at least halfway through it to get through the homework that's due on Wednesday. You're too slow. Go ahead.